Hi, a very good day to you. My name is Kai Liang from the Sustainable Systems and Devices Group. It's my pleasure today to be sharing with you the EV battery disassembly line that we have at ARTC. First up, let me start with the challenges that we have today. To look at the electrification that's happening all across the industries, in land transport, in maritime, and in the energy sectors, end-of-life battery management has become a critical issue. The current practice is at the end of life of batteries, they will be disassembled, tested, and repurposed or recycled. Regardless of the end of life pathways of these batteries, the batteries will have to be first disassembled. And that is the focus of our development here and the line that I'll be introducing to you today. When it comes to EV battery disassembly line, there are three key challenges that we have to address. The first relates to the safety when we disassemble the batteries. The second is productivity. Currently, the batteries are in low volume. We do not see a lot of this coming to the end of life within these 1 or 2 years. But in the next 3 to 5 years, the batteries that will be coming to the end of life that require management will be huge. This will mean that productivity and efficiency will be critical. The last point is standardization. When we look at the batteries across different battery makers and models, there are a lot of different variations on how these batteries will have to be addressed, disassembled, or taken apart. So there needs to be a standardization in these practices as well. In view of all the above challenges that I've mentioned, we have integrated a line with 15 use cases. Each use case represents a technology that can be used to improve the safety, efficiency, or productivity of the battery disassembly and testing process. Without further ado, let us go into Station 1 to look at what are some of the use cases that can enable an automated and safe disassembly of battery packs. The first use case that we will illustrate is automated pack disassembly. When it comes to automation, fixed input and fixed output is usually the requirement for easy programming of robot motions. But in the case of disassembly, you tend to receive batteries of different models, types, and variations. This means that the disassembly robot would need to have a very intelligent method to decide what tools to use and how to perform the disassembly. In our disassembly robots, we have integrated cameras and vision systems into the end of arm 2. What this means is that before any disassembly action, the robot will first capture the image of the surrounding. With that, an image detection algorithm will be run at the back end so that the robot can recognize the items and components on the battery, such as bolts, nuts, or bus bars. With accurate recognition of these objects, disassembly can then take place with the robot moving to the exact location. Now, in addition to the intelligence that we have integrated onto the robot, we also need many different types of end-of-arm tools for robot disassembly process. Now, what we are showcasing here is another tool, which is a suction gripper that can be used for intelligent pick and place of components such as brackets or modules. More development on the end-of-arm tools will be required for the disassembly robot to be more capable of performing intricate tasks. Unfortunately, not all EV batteries can be disassembled by robots easily. There are many challenges to disassembly through automation. Components such as bus bars, wires, and connectors are challenging to be removed by robots. When human operators come in, they have to handle battery of different models, types, and designs. This will pose a challenge to them as they have to understand how to disassemble each of these easily. In this solution, we have introduced the digital SOP through a virtual reality headset. What this means is that operators can simply wear a virtual reality headset and follow the step-by-step guides provided by the software. To achieve this, we have modeled the CAD model of the batteries onto the software platform and also the step-by-step instructions overlaid onto the battery models. This will help to improve the efficiency and safety during the disassembly process. In addition, for operators, it can be used as a refresher or a training session to onboard new battery models and designs. The third use case that I'll be introducing is the autonomous mobile robot. Now, in a modular line such as the one that we have designed, it is important to have flexible transfer of materials in between each cell or station. Autonomous mobile robots would be a great solution for such a flexible material handling. Now, let's follow the module from station 1 to the station 2, whereby it will be discharged and further disassembled. Welcome to station 2, module discharging and disassembly. A module can be as heavy as 10 kilograms. For operators, this can impose a lot of strain on their muscles and can lead to easy fatigue over time. And that is why the first use case we have here is an exoskeleton. The exoskeleton can help to improve the support to the muscles of the operators and lead to a much better working condition and ergonomics. The next use case I will introduce here is digital SOP via ARTC. This is slightly different from the virtual reality headset solution that we have seen previously. In the ARTC scenario, the object has to be small enough to be fitted onto a workbench. A projector and a motion sensor will then be deployed to project the instructions to guide the operators through. Such a solution will ensure the safety and efficiency during the disassembly process. Upon the completion of the disassembly task, a validation module comprising of the 3D motion sensor and a camera will ensure the completion of the task. The program will then be triggered to move on to the next task accordingly. Now, the cells have been disassembled and we have now come to station 3 for cell diagnostics. In conventional cell diagnostics, it requires a full charging and discharging of the battery cell, which can take up to 3 hours. For such a process, it is time-consuming and laborious. What we are introducing here is an electrochemical impedance spectroscopy technique for rapid measurement and diagnostics of the state of health of battery. Electrochemical impedance spectroscopy, in short EIS, is a powerful electrochemical technique used to characterize the electrical properties of materials and electrochemical systems. Through applying a small alternating current voltage to an electrochemical cell and measuring the resulting current response over a range of frequencies, the data is then used to determine the impedance of the system. With a healthy cell as a reference, we can easily deduce the state of health of an end-of-life battery within 3 minutes. The cell that we are measuring here has 76% state of health. So in summary, what we will have from the end of this line is cells with a known state of health condition all the way from the start where we have a battery pack coming into the line.